Okay, so for our thermochemistry tutorial, today we are moving on to, I would say, the second half of the shapes and polarity kind of question. This one tacks on quite frequently with it. When we complete this tutorial, we will now be 2/3 of the way through thermochemistry, and there's only one question left that I need to cover the material for. So that's good. We've chomped through this really quickly, which is good. So let me actually recap some stuff from year 12 chemistry, just so you can see how it all ties together. So if you guys remember with year 12, the structure and bonding, yes. There were 3 questions with structure and bonding, if you guys recall. There was the first one, which was on Lewis structure, shapes, and polarity. There was the enthalpy question with those calculations, which that's the last section we haven't done yet. And then there was the types of solid question. You guys may have picked up that I haven't done any talking about the types of solid question, and that's what today's lesson is going to be about. So it's the types of solid question, but it's been changed a bit for this year. The focus is going to be in a different spot. So if we go and think about the types of solid question, there were 4 different types of solids that you guys learned about. There were the metals, there were the ionic solids, there were the covalent networks, and then there was the covalent molecular. So that was one of the questions you guys got last year. Does that hopefully ring a bell? All right, this year in year 13, they primarily focus on this covalent molecular component, which makes sense because that ties into Lewis structure and shapes and polarity. So that's going to be the focus of year 13. And that's, like I said, for our thermo unit. When it comes to the covalent actually, let me backtrack. With types of solids, the key thing you were talking about were properties of them. So you're looking at electrical conductivity, if it was brittle, if it was soluble, what the melting and boiling points were like. The other nice thing about this year, it's only focusing on one type of solid, and it's only going to really focus on one property, which is going to be on phase changes. So that's the one, and it's only really on phase changes. So that's the good news. It really kind of narrows down and makes your life easy. When we are talking about phase changes, the ones that they like to focus on is the vaporization, which is normally annotated as vape H, and that's just talking about stuff going from gas to liquid. And the other one they talk about is the fusion one, which is going from solid to liquid. You might also see sublimation come up, so I'll write it down just in case. That one's going from solid all the way to gas. So it's bypassing one of those phases there. Are we good so far? Keep going? Okay. So, since we are talking about phase changes, we need to be talking about the molecules, and we need to be talking about the forces that are holding those molecules together. Because whenever we have a phase change occurring, we're breaking the bonds between the particles. So in this case, if you guys remember, the force that holds the covalent molecular together, when we talked about it last year, we talked about intermolecular forces. what am I doing? Covalent molecular solids is the intermolecular forces. Do you guys remember what that means, or should I draw some molecules and show you what I mean? Show up? Okay. So let's say, for example, we had carbon dioxide. Actually, I might draw them as kind of being a bit more molecule-like. So that's carbon dioxide as like a molecule. And there's another carbon dioxide in the molecule sort of form. So when we're talking about intermolecular forces, we're talking about these forces between the molecules. When we are talking about intramolecular forces, we're talking about the ones that are bonding atoms together. Let me just grab another color. So this one here is an intramolecular bond. So those were your covalent, for example, metallic, and ionic bonds, as an example. Whereas intermolecular forces are between those two molecules. Sound good so far? Ringing a bell, hopefully? Some stuff you guys did last year? Okay. The thing that's going to change for this year is that these intermolecular forces that you're talking about, you need to be more specific with them. So these guys here, for year 13, are going to become more specific, and you need to name those specific forces. So there are 3 that you will be referring to. The first one is temporary, dipole. You can use the word force or bond. Force is the more correct term, but if you use bond, I don't think they'll mark you down for it. And do you guys remember what I'm saying about dipoles? We talked about them when we were talking about Lewis structures and shapes. So a dipole is just a molecule with an uneven distribution of charge. So temporary obviously means that it's only temporary there. There's also the permanent dipole. And nestled under the permanent dipole bond are those hydrogen bonds. And don't worry, I'll go through each one and kind of explain what they are and where they would come up. So the main thing about this year is that you are focusing on the covalent molecular. You're specifically looking at the property of phase changes, so solid, liquid, gas. And you are specifically looking at the intermolecular forces and going into more detail about what type of intermolecular force you have. Are we good so far? All right. I'll move it on to the next page just to start going through each one. I do want to make a note, though, that yes, they'll probably focus on covalent molecular and phase changes, but everything from last year is fair game to ask for this year. And I have seen on some past exams that they have asked about the other types of solids and threw in that kind of spanner of work. So it is worthwhile to revise the other solids and also their properties, just in case it comes up. It's unlikely to come up because it's old material, but I have seen them throw it in there every couple of years. And we'll look at the no brain, too small collated questions, and you can see what I mean. And I think the 2021 actually did do that. So, sorry, 2020, not 2021. All right, so let's talk about where these 3 different forces come from. The first one is our temporary dipole. To grab more colors. And now I'm going to start abbreviating things because I'm lazy. So temporary dipole bond. I'm just shorthanding it because I'm It's a lot to write. So in these guys, these will arise in nonpolar molecules. So you see why they often tie it with that shapes and polarity question, because you can then bridge it on to the next section. So they're talking about nonpolar molecules. So with the nonpolar molecules, we know that, say for example, with carbon dioxide, there's an even distribution of charge, and so it doesn't have any slight positive or slight negative, because this here is slight negative, that's slight negative, but it cancels out. So we're talking about nonpolar molecules. So in most cases, these nonpolar molecules don't have a charge. I'm just going to draw an atom, a nucleus, and then some electrons floating around it. Every so often, though, those electrons will cluster into one location, and it's going to make a temporary dipole. So every so often, what's going to happen is that with our atom or with our molecule, the electrons might cluster at one side of the atom every so often and then temporarily result in a dipole. So this is going to be slightly negative and that end will be slightly positive. And that's why we call them temporary dipoles, because they only happen every so often. When this does happen, it can induce a neighboring molecule to also form a temporary dipole. So if I have a neighboring atom or molecule nearby, then this one will influence that one to also form a temporary dipole. And since this is slightly negative, it's going to push those electrons away to make that end positive and the other end slightly negative, and then forming that temporary dipole-dipole bond. So that's being more specific as an intermolecular force. All of these are still intermolecular forces. It's just now I'm being more specific about it. Are you okay with that so far? So this is a random process. It just happens because the electrons just randomly cluster. This is the weakest out of the three types of intermolecular forces. So that's because of random electron clustering. And then this one's also the weakest. And that's because, like I said, it's only there temporarily and it's not very strong. Are we good so far with that? Keep going? Okay. So that's our first one, and that's probably the more complicated of the ones. The next one we think about then is our permanent dipole-dipole. In this case, we see this in polar molecules, which makes sense because they are always going to form, they're always going to be in a dipole state. And so that one has a natural uneven distribution of charge. And we know in our last tutorial, we talked about what causes polar molecules to form and all the different layering to the answer. You first talk about, say, for example, if you have iodine and chlorine as a molecule, you look at the periodic table and you see which one's more electron negative. And with that electron negativity, it pulls the electrons slightly closer to one atom, and that leaves the other bit slightly positive. So when I have this molecule here, we have a slight negative and a slight positive end, and that slight negative and slight positive end, that dipole is permanently there. So it always has that unequal distribution of charge, and so with that, it's always going to then have these attractive forces with the neighboring molecules as well. Yep, that should be a negative sign. So that there is our permanent dipole-dipole. Can't spell today. Are we good with that so far? All right, the last one then that I have mentioned, I'm trying to grab more colors, trying to vary it up, is our hydrogen bonds. Hydrogen bonds are a type of permanent dipole bond, or permanent dipole-dipole bond. Now this one is really, really specific. It has to be hydrogen attached to oxygen or nitrogen or fluorine. If it's not one of those three elements, it's not going to form those hydrogen bonds. The thing about these hydrogen bonds is that they're really special because of two reasons. First off, we have very electron-negative elements. The other thing they have is lots of lone pairs of electrons. So that's going to make that end of the molecule really, really negative. On the flip side, the hydrogen, you have to remember, that's the simplest of our molecules. So if those electrons are pulled away from the hydrogen, it exposes a nucleus with just one proton. So that's going to make it quite a dramatic positive and negative. The example that most people use is water. I'm just going to draw a water molecule. So water section, the oxygen section of the water molecule is going to be slightly negative. The hydrogen section is going to be slightly positive. And the bonds formed between my molecules, that is the hydrogen bond. And that one's going to be the strongest. Be careful when you're writing and explaining things. You have to talk about the force or the bond between molecules. Make sure you're using your terminology correctly, because if you're talking about the if you're not using the word between molecules, then you could accidentally be referring to the bonds within the molecule. So that's why you need to be careful with your terminology. All right, I think that is most of what I want to cover first off, and then there's some of the printout notes that I need to show you guys. All right, what questions do you have so far? Are we okay? Okay. All right, can I move it? Okay. So basically you can see how this really ties into that Lewis structure and polarity question, because basically with that information you can then talk about some of the properties that it has. Like, were you good?
Yeah.
Okay.
So is that what like the question will ask you, like talk about the properties?
I'll show you the questions, but I want to give you some more information before we see those questions. All right. So I'm going to move on to those sheets that I printed out just to kind of point out some things. The first one is going to be about those temporary dipole-dipoles. So what I have here is fluorine, chlorine, bromine, and iodine. In all three of those cases, we are actually talking about the gas element. So we are talking about F2, Cl2, Br2, I2. When we're talking about those guys, not just like the element, like atom by itself, we're talking about the molecule. What do you guys notice with the melting and boiling points as we go down the periodic table? This is basically, they're increasing, aren't they? So the thing to remember about the temporary dipole-dipoles, and in fact any of the even if it is a polar molecule. The molecular weight's really important because the larger the atom or larger the molecule is, the more likely you're going to get a temporary dipole. Since I'm more likely to get a temporary dipole, I'm then more likely to get those temporary dipole-dipole bonds. And that just has to do with the fact with the larger the atom or the larger the molecule, the more likely I'm going to get a clustering that's uneven. So that's why that happens. Do you want me to write that down?
Yeah.
Okay. So larger atoms or molecules, higher MP and BP, because it's more likely to form a temporary dipole molecule, and therefore more likely to have temporary dipole-dipole bonds. Move that over. Do you guys understand all my shorthand? Okay, because I'm too lazy to write it all out. Yeah, so larger atoms and molecules have higher melting and boiling points. It just has to do with the fact they're more likely to form those temporary dipoles, and that's because it's more likely for those electrons to cluster. I should write that down. From electron clustering unevenly. So what they're going to ask you to do for this question is they'll give you probably 2 or 3 different molecules, and they're going to ask you to compare and contrast them from their boiling points or their melting points. And so this is one of the things they could ask you to compare, is their molecular weights and their boiling points. All right, can I move it? Okay, so that was the first kind of graph I wanted to show you guys. The second thing I want to show you guys has to do with the shape of the molecule. So there's 2 factors. Actually, no, there's like 3 factors. Size of the molecule, if there's any polarity, and the structure of the molecule. So we'll look at this one here first, because that one's looking at structure. So if we are looking at these guys, I see how this one's a straight chain. This one's an isomer of the first one, and it's just a branch of it. And then this third one is, again, another isomer of those first 2, and it just has more branching. So that's straight chain, that one's more branched. And then when we're looking at the boiling point, we see that the straight chain one has a higher boiling point than the branched one. Now these 2 are the same molecular formulas. These guys are isomers. So since they are isomers, they have the same mass. So the mass isn't the factor that's then affecting their boiling point. So in this case, what I'm looking for in the justification is what's causing it to then have these dramatically different boiling points. Does anyone want to take a stab at why? Yeah, Charlie.
More stable because it's not like the straight chain is more stable because it's not like.
That's a good guess, but it doesn't have to do with stability.
Is the surface uniform?
Ooh, Hannah's gotten closer.
Because you know it's flat.
It's flat.
So it's all like
It can stack. Flat, so it can stack. Yeah, so it has to do with the fact that the straight chains are more likely to compact with each other. They got more, so if I have straight chain molecules like this, they're more likely to form those temporary dipole bonds. So you can get closer together, there's more potential layering and stacking. If I have a branched molecule, they won't be able to get as close together. So there'll be fewer temporary dipole bonds. So that's the reasoning why.
So you could fit more of that than you could of that.
Yeah, so like we're going to be able to fit more of those together. They'll have probably a higher density as well. So that's, again, like another common question. They'll give you isomers of things, and they'll give you stuff that's branched and stuff that isn't branched. And you're just talking about the fact that this is straight chain, it can do more stacking, and there's more potential for temporary dipole bonds. And get closer. And that's always the key whenever we're talking about melting and boiling points, is how many of those intermolecular forces I can get. You okay? Okay. Keep going. Okay. I want to show you guys another example of how they might ask this question and what they might ask you to compare and contrast. So in this case, what we have is acetone and isobutylene. When we're looking at these guys, I looked up the masses for you guys. Acetone, I believe, was 58, and isobutylene was 56. So they have very similar masses. So again, we're not going to be going and using this justification to explain what's happening because their masses are very similar. In this case, we are comparing basically a nonpolar molecule and a polar molecule. So this one here will be able to have that permanent dipole, whereas this one only can do the temporary dipoles. So that one, when it comes to the comparison, has to do with the type of the intermolecular force. So that one's polar. That one is nonpolar. So this one would only have your temporary dipole bonds. This one would have your permanent ones. And we know, as I was talking about previously, those permanent dipole bonds are the stronger of the two. And they're more likely to be there.
So the temporary ones are more stronger.
The permanent ones. Yeah. Oh, did I? Sorry. So the permanent ones are stronger and they're more likely to be there, whereas the temporary ones are less likely to be there and they're not as strong. The polar molecules can have some temporary dipoles because it can have that unequal distribution of charge as well. But the main thing that you're looking for is that permanent dipole. And if I had a molecule that had hydrogen with one of those three elements that I talked about, then you would say it has hydrogen bonds, which make it even that bit stronger. So that's what you're looking at when you're comparing and contrasting. So they will likely have a question comparing boiling points or comparing melting points. And they could give you a variety of things. It could be based on mass. It could be based off of the shape. It could be based off of polar and nonpolar. All right, one last thing for me to show you guys is the phase change graph. This has popped up a couple of times. It's just basically the same material, just shown visually and what's happening with the phase changes. I quite like it because you can actually see that there's a solid point, and then you have that flat line of the melting point, and then you have the next phase, which is your liquid, a flat line again to show the boiling point, and then your gas. One of the things to note or observe when you're looking at this diagram is that the temperature will increase, and then it'll stop increasing at a point, and then it'll start melting, and then it'll increase again when it's at liquid, and then it'll stop again, and then it'll increase. The thing that we need to think about is, why is it just leveling out in these locations? The reason why it's leveling out at those locations, actually let me backtrack. When we're talking about temperature, we're talking about how much energy those molecules have and how much they're moving and vibrating. So when we heat something, that heat energy is going to go into that vibration of the molecule. When I hit something like the melting or the boiling point, instead of that energy going into vibrating the molecules, it's going to be going into breaking the intermolecular forces. And since the energy is going there, instead of the movement and the kinetic energy, that's why the temperature stays at that one point for a while, and then it will phase change and keep increasing. So something just to note is that at those locations, the energy is being used to break bonds. And once those bonds are broken, we're able to move to liquid and gas. The other common question they ask is comparing and contrasting why does it take so much more energy to get something to the gas state than to the liquid state. And in that case, it's because for the gas state, we need to fully break the bonds, whereas in the liquid state, there's only some of the bonds that are being broken. To get to gas, need to break all bonds. Because what I want to do is basically just release the particle so it's by itself. So that commonly comes up. I'm trying to think what else might come up with that. It's usually that when it comes to if you see a diagram like that on the exam. It's just referring to, basically they might ask you to explain this part. They might ask you to explain why some of them require more energy than others. So I just want to show you what it looks like in case it comes up. All right. What questions do you guys have? It's nice in a sense that you don't have to cover as much content. But like I said, every so often they do throw that in there, the old stuff from last year. So do look at it. What I'll do is I'll pull up the No Brain Too Small so you guys can see that. So we can see the collated questions. I don't know if they've put in the ones for 2020 and 2021 yet. Here we go. Yes, they did. So we want the attractive forces between atoms, ions, and molecules. That's the one for this question. I'll just zoom it up so you guys can see it. So you can see in this question here, I think this is the one I might have given you guys as your, no, I gave you the 2020, sorry. You see here that they've given you the same molecule, but they're asking you to compare and contrast the vaporization versus the fusion. So fusion's talking about melting it to a liquid, vaporization is going from liquid to gas, and they're asking you why are they both positive? So they're both going to be endothermic reactions because we need to put in energy to break those intermolecular forces. And why is vaporization more than the fusion? Well, it's because we have to fully break all the bonds to release the molecules completely. And you could also refer to, like, is this a nonpolar molecule? Are they temporary dipole-dipoles? Are they permanent dipole-dipoles? That sort of stuff. And this second question here, again, very similar things. This is from the same exam. They have the vaporization again, so we're talking about liquid to gas, and they've listed how much energy you need in order to do that. And they want you to list out the attractive forces, just like I was talking about those three examples. And they want you to basically explain why is the propanoic acid the highest energy requirement. So it has to do with the fact that it's a polar molecule. This is the one that I gave you guys for homework. And again, you see boiling points coming up quite a bit and attractive forces coming up. This is what I wanted to show you. Every so often they throw stuff from the previous years into the exam, and they did that during 2020, which is kind of cruel considering it was a COVID year. But you see how they have calcium bromide has a higher boiling point than both bromomethane and bromine. So they've tossed in an ionic compound. So you do need to access some of that previous year's information. If you're trying to study strategically, I said they'll probably won't ask anything about electrical conductivity. They'll probably just focus on the boiling point or melting point. And you see how this one here, the graph that I was talking about. So yeah, just keep that in mind. But most cases, they're going to be choosing molecules so that way you can talk about hydrogen bonds, you can talk about temporary and the permanent, because that's the new material for this year. And basically asking you to explain why that is. I'm just trying to think. Oh, here's the one I wanted to show you. In this case here, you're going to be thinking both about the type of force there and also the mass of the molecule. So we see here we have methanol and we have propan 1-ol. So both of them have that polar molecule and permanent dipole dipole bonds, but in this case, we're looking at the masses and how the mass is going to allow for more intermolecular forces to form. Whereas in these two have a similar mass, so that's not the factor, but in this case, you're looking more at the overall molecule, and this one here will be able to do the hydrogen bonds, and this one won't. So yeah, that's basically what you're thinking about when you're looking at that. You see here they gave you decane, which is a very long straight chain molecule. So again, you're weighing up between the mass and the boiling point. This one has a similar mass, or the same mass, but a much lower boiling point because it's a smaller molecule. It's a polar, smaller molecule. So just because something's nonpolar doesn't automatically drop into the category of it's going to be the lowest boiling point. It depends on multiple factors. So yeah, that is what we're looking at for this section of question. So yeah, I like the no brain too small because you can just see how it's been asked different ways. And you can see there's a real focus on melting and boiling point, more so melting point than anything else. So it's nice that you don't have to study all the properties anymore. And then these are from the older exams that aren't as relevant, but might still pop up. And that's the answers. All right, that's basically it for today's tutorial. What questions do you guys have? Good? Okay. Cool. I'll stop the recording. I'll let you guys have the remainder of this session to get some work done.